Welcome to our Quantum Explorer STEM Clubs Session 2. In this session, you will explore an important concept of quantum physics known as quantum spin. We will do activities with spinning tops and gyroscope to understand this concept. The application of quantum spin in our daily lives will be demonstrated by knowing the science behind MRI scanners and by illustrating the importance of quantum spin in the functioning of these medical devices. So we will start first with subatomic particles, which are also known as building blocks of all matter in the universe. Atoms are made of subatomic particles. So electron, proton, and neutrons are all part of atoms. A subatomic particle can be a composite particle or an elementary particle. The difference between them is composite particles are particles which are composed of other particles. For example, a proton or a neutron, which are composed of 3 quarks. And elementary particles are not composed of other particles. For example, quarks and electrons. Fermions form one of the 2 fundamental classes of subatomic particles, the other being bosons. All subatomic particles must be one or the other. A composite particle, such as a hadron, may fall into either class, depending on its composition. This is a standard model of elementary particles. So you can see fermions on the left hand side and bosons on the right hand side. So fermions are further have quarks and leptons, and there are 6 types of quarks with beautiful names like up, down, charm, strange, top and bottom, and then 6 type of leptons. On the other hand side, bosons, so they are 5 types of bosons, which are also known as force carriers. Fermions and bosons behave very differently. Fermions obey Pauli exclusion principle, means no 2 fermions can occupy the same quantum state, as you can see in the picture on right hand side. Bosons tend to stay together in the same quantum states. So that's one of the difference between fermions and bosons. To understand more about these subatomic particles, the students can play a board game. So here is a link, and your teachers can print a few pages, and then students in groups can play it. So there are instructions available on the website that your teacher can tell you. So now let's move on quantum spin. What is spin? Physicists also have another word for it. It's angular momentum. Momentum is a combination of mass and speed. I feel it when I smash my fist into my palm like this. Angular momentum or spin is rotational momentum. The Earth has spin because of its mass and rotation. When certain elementary particles move through a magnetic field, they are detected in a manner that suggests they have a property of little magnets. In the classical world, a charged spinning object has magnetic properties that are very much like those exhibited by these elementary particles. Physicists love analogies, so they describe the elementary particles too in terms of their spin. Unfortunately, the analogy breaks down, and we have come to realize that it is misleading to conjure up an image of the electron as a small spinning object. Instead, we have learned simply to accept the observed fact that the electron is deflected by magnetic fields. If one insists on the image of a spinning object, then real paradoxes arise. Unlike a tossed softball, for instance, the spin of an electron never changes, and it has only two possible orientations. In addition, the very notion that electrons and protons are solid objects that can rotate in space is itself difficult to sustain, given what we know about the rules of quantum mechanics. In 1920, two physicists, Stern and Gerlach, of the University of Hamburg in Germany, conducted a series of important atomic beam experiments. Knowing that all moving charges produce magnetic fields, they proposed to measure the magnetic fields produced by the electrons orbiting nuclei in atoms. Much to their surprise, the two physicists found that electrons themselves act as if they are spinning very rapidly, producing tiny magnetic fields, independent of those from their orbital motions. Soon, the terminology spin was used to describe this apparent rotation of subatomic particles. Spin is a bizarre physical quantity. It is similar to the spin of a planet in that it gives a particle angular momentum and a tiny magnetic field called a magnetic moment. Based on their known sizes of subatomic particles, however, the surfaces of charged particles would have to be moving faster than the speed of light in order to produce the measured magnetic moments. Furthermore, spin is quantized, meaning that only certain discrete spins are allowed. This situation creates all sorts of complications that make spin one of the more challenging aspects of quantum mechanics. In a broader sense, spin is an essential property influencing the ordering of electron and nuclei in atoms and molecules. Spin is likewise an essential consideration in all interactions among subatomic particles, whether in high energy beam particles, low temperature fluids, or tenuous flow of particles from the sun, known as the solar wind. Indeed, many, if not most, physical processes, ranging from the smallest nuclear scales to the largest astrophysical distances, depend greatly on interaction of subatomic particles and the spin of those particles. Now let's discuss the differences between classical spin and quantum spin. In classical mechanics, spin usually refers to the spin angular momentum of a macroscopic object, such as spinning top or a rotating wheel. However, in quantum physics, quantum spin is a fundamental property of subatomic particles, and it is an intrinsic property of these particles and cannot be explained by classical physics. Quantum spin is a quantum mechanical phenomena and is not related to actual physical spinning of particles. In classical mechanics, the angular momentum of a spinning object can have any value and is not quantized. It depends on object's mass, shape, and rotational speed. Quantum spin is quantized, meaning it can only have a certain discrete values. For example, electrons can have only two values, either plus half or minus half. Classical spin in macroscopic objects is observable in everyday life. It affects the way objects behave when they spin, such as the precession of a spinning top. Quantum spin, being a property of subatomic particles, is not directly observable in the same way as classical spin is. Instead, its effects are observed through measurement of particle properties, such as the interaction of electrons with magnetic field, which is governed by their intrinsic quantum spin. So, how quantum spin was discovered? Here is a little video that can explain the origin of quantum spin. So how we can draw spin? So physicists use a right hand rule. So this thumb is telling us whether the spin is up or down, and these curling fingers are the spin direction. So here, if you can see, so this is the direction of the spin. So something is spinning in this direction, and the thumb pointing upward is telling us it's a upspin. And then we can you can ask students to create a spin down with by using the same right hand rule. So it is now time to do some activities with spinning tops and gyroscopes to explore the concept of quantum spin. In the next slide, you will see a video with a detailed description of how to do different activities. So please see the video first and then do all the three activities as mentioned in the video. So you learned from three different activities that spin can add, spin can flip, and spin can precess. So this is how you did an activity gyroscope to see spin precession. Many spins can align and can be made to precess. We look at the microscale in the second half and how we can use these ideas to find cancers or other medical issues. Spins can flip. This means that the rotation direction changes. Try using the right hand rule here. What was the spin direction at the top? Then the spin direction at the bottom. Spins can flip when an external force is applied in some circumstances. What did you do to flip the spin of the bike wheel? We will be looking at spins and spin flips later on. Spins can add together. When we stack the spinning tops, they kept spinning. Where is the spin arrow pointing for each of these images? What happens when the tennis balls meet? Will they spin more, less, something else? Now we will see quantum science behind MRI scanners. Here is a short YouTube video that you can play in the class and students can see. So what happens when we are inside the MRI scanners? Because of spin precession, MRI machines with their giant magnets allow us to see inside the human body. Our bodies are 65% water, and hydrogen atoms in water molecules make water interesting for MRI. Each spinning hydrogen proton is like a tiny magnet that is made to precess. At any moment in time, all the countless billions of hydrogen protons in our bodies are in random position and spinning on their axis. But inside an MRI scanner, the axes realign with the scanner's stronger magnetic field. Some will align up and some will align down, while still spinning around their own axis. There are always just slightly more up protons than down. Hence, these tiny magnets almost cancel each other out, leaving only the magnetic field from the small proportion of extra up protons. And it is this small magnetic field that we can measure using MRI. The concepts of axis realignment and precessional frequency are important when we use MRI to measure the signal from these hydrogen molecules. So how do we obtain an image from these spinning flipped hydrogen proton in the brain? When the radio waves pulse is turned off, the proton flip back and realign along the MRI magnetic field, giving off energy. Different tissues in the body give off different amounts of energy, and this energy is used to gather information about the body.